Welcome to Quideo number 5. Okay, starting with the basic question. It gives us this chart of estimates of daily intakes of calcium in milligrams for 38 women between the ages of 18 and 24 years. So we have this chart here that gives us all the data. And what I did was I put them all in the calculator first. And then I used that data to plot the histogram for part A. So we see we have the frequency on the side there, and then the calcium intake on the y or on the x-axis. And using that distribution, we could see that the histogram is approximately normal, with probably 2 possible outliers right there, and that the center is between 900 and 1100 milligrams. And the data has a large spread because it spreads about 2,000 milligrams over the whole course of collected data. So that's part A. Part B asks for the mean, the standard deviation, and the standard error. So like I said, I plugged it into the calculator using the list, and then I went to calc and then one variable statistics, and it just gave me all these. So the x bar is 926.0263. The standard deviation is 421.5706. And then it asks for the standard error. So standard error is standard deviation over the square root of n. So once you plug that in, you get that the standard error is 68.3878. Okay, part C says find a 95% confidence interval for the mean. So when you're using a mean, you're going to use Z star for your confidence interval. So the formula is x bar plus or minus Z star times the standard deviation over square root n. And we get the Z star value of 1.96 because that's the standard value of 95% confidence intervals, which you can find in the table at the back of the book. We're going to assume an SRS and that it's independent, and we have over 30 observations, so it should be approximately normal. So once we plug all our values in, we get that the range is 791.99 to 1060.07, and that just means that we are 95% confident that the daily intake of calcium in women aged 18 to 24 is between 791.99 milligrams and 1060.07 milligrams. So part D said to take out the 2 largest values and then refine the confidence interval. So the 2 values that you take out are going to be 2,433 and 1,933. So once you do that, you just refine all your values in the calculator like I did up there and replug everything in your formula. Then you get that the confidence interval is 766.39 to 963.99. And what that means is we are 95% confident that the daily intake of calcium will be between 766.39 milligrams and 963.99 milligrams. And we notice that our sample size is a bit smaller. The n is only 36 as opposed to 38, and that means that our range is going to be smaller as well, because variance decreases as the sample size decreases. Okay, the advanced question. You play 2 games against the same opponent. The probability you win the first game is 0.4. If you win the first game, the probability you also win the second is 0.2. If you lose the first game, the probability that you win the second is 0.3. So question A asks, are the 2 games independent? And I said that no, they're not independent, because the outcome of the first game influences your probability of winning or losing the second game. Part B says, what's the probability you lose both games? And part C says, what's the probability you will win both games? So I made this little tree here in order to calculate all the win-loss ratios. So losing both games, first you go on the first loss path right there, and then you multiply it by the second loss path right there. So you do 0.6 times 0.7, and you get 42% chance of losing both games. And for winning both games, you just do the same thing with the winner path right there, and you get 0.4 times 0.2, which is 8%. Part D asks you to create the probability model. So you make this little table here with all your scenarios that you could possibly have, and then you do number of wins and then the probability that you will have that amount of wins. And you subtract your expected value from that number of wins in order to get your deviation from that. So next, we have to calculate that expected value and standard deviation. So to do the expected value, you just multiply all of the probabilities by how many times they can appear, or how many wins you would have. So we have 2 times 0.08 plus 1 times 0.5 plus 0 times 0.42, and that gives us 0.66, which is what we subtracted from the wins up here to get our deviation from mean. Next, we have to do the standard deviation. So to do that, you do your var x, and then once you get that, you have to square the deviation value and multiply that by the probability again, then add all those together. Once you get that, you can find the standard deviation by doing the square root of the var x, which is 0.62. Alright, now for the AP question. So we have these U.S. Department of Agriculture guys trying to compare methods of finding E. coli bacteria levels in beef. So we have these two different methods, and then we have how much E. coli they found with those methods down here in this table. And we're just doing a significance test to see if the methods are different or not. So the best way to do this, of course, is to use our phantoms. So the P, the parameter, is differences in mean and amount of E. coli in millimicrobes per liter of ground beef. Our H, our ho, and our ha, we have that the mean of method A will equal the mean of method B, and our ha is that the mean of method A will not equal the mean of method B. And the mean of method A is just the mean amount of E. coli found in method A, and the mean of B is the mean amount of E. coli found in method B. For A, we have to assume, we have an SRS, and we assume independence, and since n is 10, that means that we can assume normality. Our n, our naming, we're going to be using a two-sample t-test in order to find our probability. So we have bar xa minus bar xb minus mean A minus mean B over the sample standard deviation of A squared over the sample size of A plus the sample standard deviation of B squared over the sample size of B, and then you square root that whole thing on the bottom. So here's all the values that I got. Again, I just plugged them into my calculator and then did one variable statistics to find both of them. And then we also have our degrees of freedom, which is 10 minus 1, and that's going to be 9. So once you plug in all those values, of course you have 0 for the population mean, because that's what we're testing against. You plug in all those values and you get that your t-value is 0.7233, and that is going to be between 0.2 and 0.25 once you go with your degrees of freedom in your t-table. But since this is a two-sided test, because we're using the ha of not being equal to right there, you have to multiply that by 2 in order to, and then you get your p-value of between 0.4 and 0.5. Which means we fail to reject the ho that the mean levels of E. coli found in each method will be the same, because our p-value is between 0.4 and 0.5, which is way over our alpha value of 0.05, so the data is not significant.